So if we start off like this, H2O liquid, those activities don't change. And so let's just ignore those. But let's say if we have no collisions yet, and then we let the water molecules collide. This is hypothetical. So we get plus X molar here, plus X molar here. And then at equilibrium, we'll have X molar here and X molar here. Then what we want is we want to know what the K for this reaction is so we can determine what X is. Or we need to know what X is in order to determine what K is. And so we do H3O plus here and hydroxide. Okay, so what we're going to do is we're going to determine K here. And it turns out that we can measure the pH of this. Let me do this here, save this. All right, so we'll just experimentally measure the pH. And the pH comes out to, just using a pH meter, 7.00. All right, so we can convert the pH to a concentration. And so this is our raw data here. Here. And the concentration is going to come out to, this is the power, or the exponent. And this is going to tell us something about the coefficient here. So actually this translates to 1.0 times 10 to the minus 7. Power function here. Okay, so this exponential term is this here, and this is going to be related to the coefficient here. That is, we're going to have 2 sig figs here, coefficient. If this is 0, that means it's right on 7, but if it's non-zero here, then it's between, let's say, 10 to the minus 7 and 10 to the minus 8. As this number grows bigger, it gets closer and closer to 8. And so the stuff after the decimal will tell us, where we are in relation to it. Is it halfway between 7 and 8? That would be 5. But a 7.5 is not, because it's not linear. And so if I had a pH of 7.5, that's not necessarily in between. It's just the way it works. The halfway point. All right, so that means we have here 1.0 times 10 to the minus 7 molar. Because what the pH measures is it measures the equilibrium concentration. We could have the initial pH recorded, but that would require, a different type of reaction. Okay, and then this is, because it's a 1-to-1 ratio, it's going to be 1.00. Excuse me, 1.0 times 10 to the minus 7 molar. So we plug that in here, we're going to get 1.0 times 10 to the minus 7 molar. We drop the units because we're looking at activity squared. And so this comes out to 1.0 times 10 to the minus 14. Now, the temperature is important because at higher temperatures, we're going to get more hydronium. At lower temperatures, we're going to get less hydronium. And so this is going to be at 25 degrees C. And this will be KW. This is called KW for water. And so this is the water ionization constant. what happens with temperature is if we increase the temperature, the pH changes. So, let's see here. This is the temperature and pH of water. If we increase the temperature, the pH changes, and actually the pH goes down. And that means Kw will change too. Kw goes down. If we decrease the temperature, the pH goes up, becomes less, and the Kw goes up here. So that means that water is pH 7 only at 25 degrees C. At other temperatures, the pH changes. But that is difficult because can you tell me what the pH of pure water is at 23 degrees C? No. I mean, you can. You'd have to just measure it or figure it out. So instead, what we do is this. As the pH changes with temperature, there used to be a little knob on pH meters. And this little knob is, you just change the dial so it keeps reading 7. So if the temperature changes and the pH drifts a little bit this way or that way, then you twist this knob and it just readjusts the meter. And so that's called a temperature correction. And so modern pH meters just do this automatically. That way, water is pH 7 at all temperatures that you work at. And we don't have to memorize what the pH of water is at different temperatures. We just say the pH of water is pH 7 because we have a temperature correction. So we'll just add that here. Modern pH meters have a temperature correction so that water's pH, pure water's pH is 7. It was always 7. When I say water, we have to be careful with what type of water we're talking about. Because our DI water, what was the pH of DI water that you got out of the tap? I did the wrong page. The DI water in the lab is contaminated. Do you know the difference between DI and DW? DI is deionized water. Do you know what DW is? Distilled water. Do you know we don't have distilled water? It's too expensive. Distilled water is like, I don't know, maybe $1 a gallon, you know. Whereas deionized water is a lot cheaper. Not a lot cheaper, 60 cents a gallon. And so the DI water in lab is contaminated with what? CO2. aqueous. Do you remember Henry's law? Air contains CO2 gas. And it depends on the partial pressure of Henry's law. Henry's law just says that the concentration of the CO2 in water is equal to the Henry's law constant. So I think they give the symbol K times the partial pressure of CO2. And so the more CO2 we have in air, the more CO2 will dissolve in here. And we know that CO2 reacts with water in a Lewis acid-base reaction. Could you draw the mechanism of the Lewis acid-base reaction of CO2 and water for me? Let's say if I asked you on a test, would you be able to do that? Yeah? I'll draw the mechanism of CO2 reacting with water. In other words, not that I would, but I have in the past. It doesn't ring a bell, or it rings a bell? When we do Lewis acid-base reactions, it's a bit more work because we have to identify each atom as a potential Lewis acid or Lewis base. Do you remember doing this? The oxygen's a Lewis base, the carbon's a Lewis acid, the oxygen here is a Lewis base, and then water. So people ask me what to study, or I need to post some stuff, but I think the most important thing to study initially is the notes. Can you do everything in the notes? You don't remember this? There were two options. What were the two options? Option one was what, and option two was what? What if this were a 25-point question on a 100-point exam? This is the type of stuff I've had. UCLA, you don't want to. The UCLA, it's not like I give a lot of questions to, but I remember most of my tests at UCLA weren't that many questions, 4 questions. I had a lot of exams with 4 questions. Each question worth 25 points. If you didn't know it, then you're kind of screwed. And they pick obscure stuff, of course. This is not obscure because this is direct from the notes. This should be like what we call just recall, recall memory. It's nothing new. It's nothing like where you have to come up with some kind of new idea or something like that, or you have to use recalled knowledge to come up with some alternate thing. But the two mechanisms were that the oxygen on water attacks the carbon on CO2, or alternately, the oxygen on CO2 attacks the hydrogen on water. But, this is the first, if we're preparing for tests, this is the first thing to do is to make sure you understand the notes. If there's something that's not clear in the notes, get it cleared up. And preferably get it cleared up, well before the test so that, it's well established in your neural, networks or whatever, connections. But anyway, I'm going to continue on here. Due to this mechanism, what does it ultimately produce? CO2 and water ultimately produce what? Carbonic acid. And therefore, the pH of our DI water is around 4.5 or so. The pH is around 4.5. If you took a straw and blew bubbles in the water, the pH would go down even further. It'd become more and more acidic. If you boil it, what happens when you boil it? This is why we boil the DI water, but it's kind of futile in a way. It's futile because we boil the water to purge the CO2 out of the water. But the problem is okay, I told you to cool it down. As you cool it down, what's going to happen? It's just going to reabsorb the CO2. So when you cool it down, you're supposed to cool it down in an air or CO2-free atmosphere. And so really what we should have done, I don't know if the nitrogen tap was working. Most labs have a nitrogen tap. And so what I would have done, we don't have a nitrogen tap. Because most labs have a nitrogen tap because they have a huge tank of liquid nitrogen sitting next to the building. And this huge tank of nitrogen is constantly boiling because nitrogen has extremely low boiling point, like minus 90 Celsius. And so they don't want all that nitrogen gas to go to waste. And so what they do is they just pipe it into everybody's lab. So we get free nitrogen in the lab. We don't have to buy a tank of it. And so what I would have done is I would have just gotten a hose, purged out all the air out of there, and then just capped it with nitrogen. And that would have prevented CO2 from reabsorbing due to Henry's law. So this is why it was kind of futile. It's kind of nice to do. The other alternative is if we put it in a bottle and we make sure that the head space, that is the amount of air left in the bottle, is minimum. We fill the bottle all the way to the rim and then cap it. And that way we'd get minimal reabsorption of CO2. And then when we're ready to measure the pH, we'd pour that immediately and try to do it quickly. Because with time, the pH is just going to drop. It's not going to stop dropping until it's reached equilibrium. And the equilibrium would be, once we have enough CO2 in there, the absorption rate into what we call a dissolution rate or absorption rate of CO2 gas in there is equal to the desorption rate, of the CO2 leaking out of there. And then the pH will stabilize. Okay. But that's our DI water, and so usually the stockroom does it for us. I don't know why they didn't have it. Normally we have a bottle of boiled deionized water in the lab that's capped. But yesterday we didn't. It would have been better. The stockroom had boiled it and then sealed it to try to minimize it. And then maybe blow some inert gas in there. All right, so from now on, for all these kind of pH calculations, we're going to be working at 25 degrees C. We don't want to have to do any fancy corrections or whatever. And so let's just work at 25 at room temperature. Because the way the pH meter does it, it's artificial, right? All it's doing is it's moving the dial or the scale so that it always lines up with 7. Now, the pH is naturally changing. And so if we weren't working at 25 degrees C, then we should do something to correct that. And if we work at 25 degrees C, then I'd like you to memorize this. I'd like you to memorize that the pH of pure water is what? 7, and it's real 7, that's a real 7. And that KW is what? KW at 25 degrees C is 1.0 times 10 to the minus 14. Now, the pKW for this is easy. The pKW here is equal to 14. And it's right on 14. because it's 1.00, I mean to 2 sig figs. So we say it's right on 14 to 2 sig figs. So this has 2 sig figs because the coefficient has 2 sig figs. And the exponential term here, that has no sig figs because that just tells us how many spaces to move the decimal point. And so this is a pKw. In general, what we have is, for power functions, we call px. Px is, let's say the coefficient were not 1. Let's say the coefficient were 1.3. If it's 1.3, then it's between 14 and when we get to 10, it's between 14 and 13. Because when we get to 10 times 10 to the minus 14, 10 times 10 to the minus 14 would be 1 times 10 to the minus 13. So it'd be between there. So it's somewhere, and it's not linear. So what we do is in general, when we want to get a px function, we take the negative log of x. So, for example, the pkw is equal to the negative log of kw. The pH is equal to the negative log of the H plus, or hydronium. I'll just call it H plus. And the POH is equal to the negative log of the OH minus. We could reverse this. Let's say we want to go and figure out what X is. If we want to figure out what X is, then we just use a little bit of algebra. We take the anti-log of both sides, and we get the anti-log, which would be 10 to the minus px, molar in this case. And power functions are quite useful. So let's give like a relationship of one power function here that's quite useful. This relationship is easy to derive, but it's also easy to remember. So let's go ahead and use this here. And that is kW. Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And so we can do pKw and take advantage of the properties of logs. So the pKw is going to equal the negative log of kW. The negative log of kW is 14.00, which is equal to the negative log of the product of the hydronium ion concentration times the hydroxide ion concentration. The negative log of the product is the sum of the logs. So we do, this is going to be the negative log of the hydronium concentration plus the negative log of the hydroxide ion concentration. So the negative log of the hydronium ion concentration is the pH, and the negative log of the hydroxide ion concentration is the POH. And so this is a derivation for this, but most people just remember this formula and not derive it. If you forget it, it's easy to derive, or you can see the relationship. But the POH plus the pH is equal to 14.00. So what that means is that the POH and pH are tied together. And so what they have is they have a conjugate style relationship. You know, the conjugate style relationship, if one side goes up, the other side must go down. And so this is kind of a conjugate or seesaw style relationship. So if one side of the seesaw goes up, the other opposite side goes down. Therefore, we don't have to talk about pH and POH. We only need to talk about pH, because then we can figure out what the POH is for anything. And so typically we just look at the pH values. So the pH values are going to range from what? Do you know the range of pH values? What is the lowest pH value? I'm sorry? No. No, it's not. Not 0. I'm sorry? Not negative infinity. It doesn't go that low. These are, no, not negative 14, but so good, yes. It's going to plateau because what happens, usually our typical range is what? Our typical range, pH, I should put typical in quotation marks because that really doesn't explain it. But usually we go from 0 through 7 to 14. But if we had a pH of 0, what is the concentration? Yeah. If we had a pH of 0, the hydronium ion concentration is 10 to the 0th, which is 1 molar. If we had a pH of 3, then it's 10 to the minus 3 molar. 7 is 10 to the minus 7 molar. And 14 is 10 to the minus 14 molar. So the lowest pH is not 1. If we had a pH of 1, that would mean the pH would give a 10 to the minus 1 molar concentration. And 10 to the minus 1 molar is only 0.1 molar. If the lowest pH were 0, then the highest concentration of hydronium is only 1 molar. Can we have higher concentrations than 1 molar of acid? Yes. So for example, what we call dilute hydrochloric acid is what concentration? So one automatic question comes up, possibly. You know, dilute HCl equals 6 molar. Dilute HCl is 6 molar. That means, what is the pH? The pH is equal to the negative log of, let's say this, you know, HCl is a strong acid. Strong acids do what? Dissociate completely. So this is 6 molar H plus. So we're just going to throw in 6 here. What's the negative log of 6? What is it? Negative 0.57? 77, thanks. So we already have a pH, I mean 6 molar HCl should be negative 0.577. What about concentrated HCl? Do you know what concentrated HCl is? The concentrated nitric is 15, 16. Concentrated HCl is like, what is it, 18 molar? 18 molar. Let me make sure. Can you stick 18 moles of HCl into one? Liter? They do it by percent by mass, 37% by mass. That's the max usually that we can get. Oh, 12 molar, sorry. What is 18 molar? Sulfuric acid? 12 molar. So what would the pH, the corresponding pH be equal to? Can somebody calculate it? Negative 1.079, thanks. So even though that's twice the concentration, well, I guess it is. It looks like it's twice that, so negative. So we're down to negative 1.079. Yeah. And so a common misconception is that the pH only ranges from 0 to 14. Is that possible? No, it's not. And so oftentimes people will ask, what's the lowest pH? People will say 0. What's the highest pH? 14. Because that's all they see. They see the scale from 0 to 14. Why is that? Why do we have this as a typical range, 0 to 14 for pH? One of the reasons why you don't see calculations like this often, do you often see calculations that show a negative pH like that? No. Or what do you think the highest pH is? It's the same thing here. If we go to sodium hydroxide, this would be 1 molar, 1 molar sodium hydroxide would have a pH here. Because the pOH is 0. If the pOH is 0, the pH is 14. But can we have higher concentrations than 1 molar? Is it possible? Yeah. What about 6 molar sodium hydroxide? What about 12 molar sodium hydroxide? Then we're in pHs around 15. And the reason for this, the yellow here, the typical range is this. What happens when you get to higher and higher concentrations? As you get to higher and higher concentrations, can you think of something that happens that you don't worry about? You start to worry about certain things that you wouldn't worry about at low concentrations. See, this is, you want to make sure you register these into your neurons so that you can make connections. You want to connect things together, and those connections take time to develop. Rebecca? Yeah, for sure it'd be more acidic and more basic. Higher concentrations of acids and bases are going to be more acidic and more basic. But there's something else that we worry about. It's more dangerous. High concentrations of acids are more dangerous, more reactive. But there's something else we worry about.
Can you not measure it if it's too much, too acidic or too basic?
No, you could measure it with a pH meter, but the thing is, our calculations here, how much confidence do you have in these calculations here? The calculations I just did. That's simple. It doesn't look I made any mistakes. I plugged it into the equation and everything looks good. How much confidence do you have in my calculations here? In these calcs? Nothing, I mean, like nothing, when we have high concentrations, nothing to be of concern of other than the safety risk? Uh-huh.
Is it that, like, when there's more concentration, there's more room for error in the calculations?
Yes. And where does the error originate from? Is the question. Yeah, you know what? I don't have much confidence in these calcs. I would have pretty good confidence in these, I'd have a good confidence in these calcs. I'd expect them to be fairly accurate. Why?
Is it like if the number gets too high, there's more rounding error?
Not more rounding error. Rounding error afflicts us everywhere, whether it's low concentration or high concentration. All right, you guys give up? Or will it come? Maybe if you walk down to Ralph's or something, it'll pop in your memory. Yeah, normally you start thinking about it, and then in your subconscious, your brain is trying to work. That's it. You might not be thinking about something, and then all of a sudden your subconscious is continuing to work on it. Maybe, but maybe not. Let me give you the answer then. These, we expect ideal behavior. These are going to start to deviate from ideal behavior. At low concentrations, the solutions behave more ideal. Over here at high concentrations, we shouldn't use the stoichiometric concentration. We must use activities. Otherwise, we can't have much confidence in these because the effective concentration tends to deviate significantly from the stoichiometric concentration at high concentrations, right? And so we aren't going to have as much confidence. And therefore, in Chem 4, all you did were calculations in the range of 0 to 14. You never did anything beyond 0 and 14 because it wouldn't have worked very well. So how much confidence in these calculations when we're using the stoichiometric concentrations and not the activities? And so we're going to have less confidence in these, so you can't have as much trust in these numbers. Does that make sense? Maybe. And so that was the connection I was trying to look for, but sometimes it takes time for that connection to pop up in your mind. And so this is why people have the misconception. People have the misconception that the pH only ranges from 0 to 14 because that's all they've ever seen, right? And so some people think it's impossible to have a negative pH because the lowest pH they've ever seen is 0. It turns out the lowest pH of a natural body is actually no, I shouldn't say natural. The lowest pH measured is in California. Come on. It used to come right up. Lowest OH, no wonder, lowest pH measured. I need to. It was from the mine tailings in California. Let me find it. Yeah. Here it is, 3.6. This is a Richmond mine at Iron Mountain, California, minus 3.6. Wow. That's the measured pH, you know, we're not doing a calculation here. You know, but if we just tried to do a straight calculation, it's probably going to be off because the concentrations are so high. So California is known for a lot of things, and this is one of them here. All right, now what happens is this. When we're doing this, when I just did these calculations, I ignored something. In the calculations for HCl, I ignored something. What did I ignore? Yeah, I ignored the chloride, but chloride is the conjugate base of a strong acid, and one of the rules that a lot of students memorize is that the conjugate base of strong acids are too weak to be acidic. I need to give you another chart, but chloride, bromide, iodide, I mean, those bases are too weak to be basic, I should say. And so we don't consider those. And so I ignored that because chloride is so weak as a base, it's fair to ignore. The Kb value is what we call very small. If the Kb value, you know, if the Ka value of the acid is very large, the Kb value is very small, which means it's kind of negligible, ignorable. But I ignored something else. I ignored something else not related to HCl. Yeah, I ignored the water because during this process, does the water stop colliding? No, the water is going to continue to collide, and that means water is going to add more H3O plus to it. And so what did I ignore? I ignored the water contribution to hydronium. H2O does not stop colliding. Some of those collisions are going to successfully produce. So actually it's even more acidic, right? Because not only do you have the hydronium from the acid, I also have the hydronium from water. So it continues to produce hydronium. So the way we typically handle this is via stepwise approach. Let me see. So in step one, we have the biggest K. And so we want the biggest contributor. And that would be HCl. HCl plus H2O liquid yields H3O plus Cl minus. And we have K for this is very, what is K? We're just going to call it very large. Very large. And so initially, I'm going to start off at, what molarity? We'll do dilute HCl. Initially, we'll start off at 6 molar. Water is a pure liquid. We're going to go 0 molar here and 0 molar here. And then there's going to be a change. If K is very large, what is the extent of the change? If K is very large, what is the extent of the change?
It's almost all of it.
Yeah. But we don't actually have a number here, so what we're going to do is we're just going to assume it's all of it. If K is very large, we don't have a very large button on our calculator. And so we wouldn't be able to calculate X. We'd like to calculate X, right? But in order to calculate X, we need a number here so we can generate an equation to solve for X. Okay, after step one, we're left with 6 molar hydronium. Now we go to step 2. Step 2, we have 2 choices. We do Le Chatelier's style perturbation, or we do a reset. So in step 2, I have H2O liquid plus H2O liquid goes to hydronium plus hydroxide. Oh, I forgot to do one thing here, and that is when K is very large, we expect this to be one-way. Reaction. And therefore, I just draw the forward arrow here, rather than a two-way, where I draw 2 arrows there. Do we worry about pure water in the ice? We don't. And so I'm going to start my ice here And just completely ignore the waters. Activity doesn't change. In pure water, what is the hydronium? Actually, I'm not going to draw the complete ice table, because this is going to be Le Chatelier. I'm going to just draw initial. Well, we're always going to be dealing at 25 degrees C for this chapter, and therefore the hydronium is what? 1.0 times 10 to the negative 7 molar. 1.0 is 2 sig figs times 10 to the minus 7 molar. All right, so this is from water, initially, from pure water. When we add the HCl, it's going to change things. And so the initial from the HCl, so this is the initial from the water, and this will be the initial from the HCl down here. The initial from the HCl is going to be 6.0 molar. How much hydroxide does the HCl give? None. 0 molar. And so now we have our total initial. It was nice, you know, it was at equilibrium. Now we perturbed it by adding more hydronium. And so now we have a new initial which is no longer going to be at equilibrium. So the new initial is going to be I need 6 zeros. So 1, 2, 3, 4, 5, 6, 1, 0 molar. Actually, I'm not allowed this many sig figs, but I'll just carry it. And this is going to be 1.0 times 10 to the minus 7 molar here. All right, I perturbed my equilibrium. Which way is it going to shift? It's going to shift. Now I have too much, right? Too much product. It's got to shift to the reactant. So this is going to be minus X molar, minus X molar. And so at equilibrium, I'm going to have, well, this is plus X, but, you know, this is pure liquid, so it's not really going to change its activity. So what we're going to do here is we're just going to focus on this. You know, this. I'll just write this up here, plus X. But we really don't worry about that. You're going to add a little bit of water. If you add a little bit of water to pure water, does it change the concentration? No. So what we end up with is 6.00000000010 minus X and 1.0 times 10 to the minus 7 minus X. Then we need to solve for X. The algebra gets messy. This is kind of messy. Therefore, I recommend to reset. What I mean by reset is this. Let's see if this comes back later. I'll just. Go to here. So what I mean by reset is this. What we're going to do is, this is our initial, and then we're going to reset to the left. Everything, or as much as we can. And so this is going to be minus y molar, minus y molar. And so I'm going to have my new initial here. This is going to be the reset initial from water. And y we're just going to have as minus 1.0 times 10 to the minus 7 molar, minus 1.0 times 10 to the minus 7 molar. And so we end up with 0 molar here, 0 molar here. So I know that water, I can't, you know, what is this on? I can't prevent the water molecules from colliding. They're already collided. But what I'm going to do is I'm just going to push them all back, you know, hypothetically, just for the calculation. And so this will be the initial from the HCl, which would be 6.0 molar hydronium and 0 molar hydroxide. And so my new initial is going to be 6.0 molar here and 0 molar here. So what I'm going to do is now I'm going to have the water hydrolyze or autoionize. Hydrolyzes itself. What's going to happen here is we're not going to get 1.0 times 10 minus 7 molar. We're going to get a lot less. You know why we're going to get a lot less? Because Kw is a constant here. I might have lost the recording here if I have to force this to shut down. And so when we look at Kw, it's the hydronium times the hydroxide. So what happens if the hydronium climbs sky high? What's got to happen to the hydroxide? It's got to go way down. And so in other words, if I already have a lot of product to begin with, I don't need much reaction to get K. And so the amount is going to be, the change is going to be quite small. This is going to be plus X. Now a lot of people think that plus X is going to be 1.0 times 10 minus 7 molar. No, it's not. Because the hydronium and the hydroxide are in this kind of seesaw relationship. And so what we're going to see is that we're going to have a Le Chatelier style inhibition of forward reaction here because we already got a lot of product here and it's trying to shift it to the left. And so at equilibrium I'm going to get 6.0 plus X molar and then X molar here. Okay, then we just solve for this. So we got 6.0 plus X times X. And I expect the change to be very small because Kw is 1.0 times 10 to the minus 14, which is very small. Well, it's small. Let's say small. It's quite small. Therefore, I'm going to use the SA for this. And 6.0 plus X is just going to be 6.0 times X. The SA is just saying that X should be much smaller than 6. And therefore, X is equal to 1 times 10 to the minus 14 divided by 6. Which is going to give us what? I'm using my phone to record this, so can somebody calculate it? 1/6. 1/6 is what, 0.2? Times 10 to the minus 14, which would be 2 times 10 to the minus 13. Or no, I make the coefficient, I make a 2 times 10 to the minus 15. What, or something like that? What is it? 1.67 times 10 to the negative 15. Did you round this?
Yes.
Don't round it yet. So what we're going to do is we're just going to call it 1.6. We're allowed 2 sig figs. So what I normally do to minimize round off error is carry at least 1 extra digit. And so I'm just going to call this 1.66 times 10 to the negative 15. Then we have to justify the SA. By calculating the percent change. The percent change has to be less than 5%. And so when we calculate the percent change, this is going to be the change x over the initial 6. So that's going to be x over 6.0 times 100%. Can somebody calculate this? Okay, thanks. That is way less than 5%. Much smaller than 5%. In fact, it's so small, I mean 10 to the negative 14, it's so small that I think this is, I'm going to have very good confidence in this. I'm going to have very good confidence in this. When I start to lose my confidence is as I get closer to 5. Let's say I'm at 4%, I'm going to start thinking, oh, my calculation isn't going to be as good. But still allowable, but not so great, you know. When I get to 5%, then I really start to worry, you know. And this is why the cutoff is at 6 or greater than 5, because if I'm greater than 5, I'm already starting to worry at 4, you know. And you got to make a cutoff somewhere. And so if you're at like 5, somebody will come up to me and say, oh, you know, it's 5.1%. You know, it's only 0.1% above 5. Why is it so black and white? And so they say, they come up to me and say, it's 5.1%. And I don't want to solve it with a quadratic equation. It's just close enough. But it's not really close enough because you're already starting to worry at 3%. You're worrying, calculation's not so great. 4%, not so great. 5% is too much pain to endure, but we'll endure it. But going to 5.1%, you know, you're asking for too much. Does that make sense? For the confidence. And so this is why the 5% is actually quite high, and the calculation isn't going to be the greatest, but that's the maximum pain we'll accept. Beyond that, we don't want to accept anymore. But this one's great because it's so small that I have great confidence that even if I use quadratic, I'd get the same answer. So this is going to be 6.0 plus 0. Okay, so this is 10 to the minus 14, so I need 13 zeros. Your calculator's not going to be able to handle this because there's too many digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 zeros and a 277. So we'll go 13 zeros and 277. And so when we add these two up, I'm going to get 6.0. Now, when we do addition and subtraction, I'm only allowed 1 decimal place here. So all these additional decimal places are not allowed, so I'm going to subscript them. So that's 1 0, 2 zeros, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 2, 7, 7.
You're using the change, not the X.
Oops. Yeah, you're right. This is it. I need 14 zeros. Sorry, not the percent change. Thanks for fixing that for me. I need 14 zeros and a 166. So here I have 1, 0, and then I'm going to subscript the second, third, fourth, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 166 molar. This is way less than 1 times 10 to the minus 7. In pure water, you know, we don't already have a whole bunch of product. If we already have a whole bunch of product, like 6 molar here, it's really going to inhibit the forward reaction. Le Chatelier's, you know, is trying to push this to the left. But it can't push it to the left because we got 0 here. But anyway, looking at this, yeah, it's way too many digits for your calculator, but, you know, we could do it by hand quite easily. And would you call that a significant addition or insignificant addition? Insignificant addition. If it's an insignificant addition, was step 2 critical or not critical? Step 2 was not critical. And so what most people do is they skip it. They say that water at the most is going to add this. At the most. But it's going to be less than this because we already have some to begin with, right? And so at the most, water is going to add less than this amount. And if less than this is like 10 to the minus 8 or something like that, is it going to make a significant, at 10 to the minus 8, that's like 7 zeros out. Is it going to make any difference? No. And so in this case, yeah, step 2 was not necessary. And so the conclusion here is step 2 was not necessary for hydronium. However, for hydroxide, we started off with nothing. And if you have nothing, then anything's better than nothing, even if it's just 1 drop, like 1 drop of water. I think, you know, it would be very valuable. And so for hydroxide, it's crucial. I mean, we're going to have 1.66 times 10 minus 15. So a weird thing happened. When you have a beaker that's labeled 6.0 molar HCl, what's in this? What's in this is we have hydronium, well, the HCl. We have HCl molecules that should be 0 molar. We have hydronium, this is going to be 6.000.166 molar, just slightly above 6. And chloride is going to be at 6.0 molar. Got to do that initially. And we actually have hydroxide in here. Where does that hydroxide come from? The hydroxide comes from water. We can't stop it from happening. And this is going to be 1.66 times 10 to the minus 15 molar. And so a strong acid like this has both strong acid, hydronium, and strong base present. And so the way we define an acid is like this. Definition of acid is that the hydronium concentration must be greater than the hydroxide because acids have both hydronium and hydroxide present. And so here it's negligible, here it's significant. Or maybe it's negligible, it depends on how you want to do it. But this is significant. And so this is what we're going to call the inventory of this solution. And the pH, what is the pH of this? We got is the negative, whatever, it's negative 0.5. pH was equal to negative 0.5. This is a power function, so it was 0.57. We're going to round it to 2 sig figs. 2 sig figs. Okay, what I'd like you to do is I'd like you to determine this here. we're going to have a beaker that's going to be labeled 1.0 times 10 to the minus 8 molar HCl. What is the pH of this? Do you know the pH scale? Some people will say the pH, the power of the hydronium concentration is 8. But they don't know the pH scale, because the pH scale is this. pH scale ranges from more than 14 to less than 0. But 7 is neutral. 14 is quite basic, strongly basic, we say. And 0 and lower, this is strongly acidic. So a pH of 8 places it into the moderately basic range, or weakly basic. Actually, we'll call this weakly basic. So some people will say the pH of 10 to the minus 8 molar HCl, that gives us 10 to the minus 8 molar H plus, which is pH 8. But pH 8 is weakly basic. How is this solution basic? It's an acid. There's no base. And so this is wrong. What am I missing? Well, do this calculation. Do the calculation for this HCl solution. You know what's wrong? I'll tell you what's wrong. They're ignoring something. What are they ignoring? Water. Over here, with 6 molar, can you ignore water? Sure. If we're only interested in the pH, did it change the concentration much? No, so we can ignore water. But in this calculation, we can't ignore water. Water's going to water's going to be a bigger contributor to the hydronium in relative terms. And so you would set it out the same way, and then we can calculate the pH of it. The pH, I mean, it's 10 to the minus 8 molar is very dilute HCl. So when you have a very dilute solution, the pHs converge on what number? As the solutions become more and more dilute, they become more and more like pure water. As they become more and more like pure water, the pH converges at pH 7. So very dilute bases and very dilute acids will ultimately go to 7 as you increase the dilution. But what I want to know is I want to know the correct pH for this. It's not pH 8. What is the pH for this? So you'll have to figure that out. What time do we go till? 11? Oh, we have 6 minutes. All right, why don't you work on this calculation now?
K value smaller, do you want us to find it?
I'm sorry?
Do you want us to find the K value, or we're assuming it's small?
K value of what?
The thing we're doing?
Oh. K value small. What K values do you need for this calculation?
I don't know, maybe I don't. I'm sorry.
Well, when you get there, let me know, and I'll tell you. But there's no, this K value here is small, but we don't use small. We use 1.0 times 10 to the minus 14. This is the K value. KW I want you to memorize at 25 degrees C, is what I mentioned earlier. And also, the K values for strong acids are easy. What are the K values for strong acids?
Very, very small.
Not very, very small.
Very large.
Very large. When you have a K value very large, what does that mean? And so I tried to show it with the arrows on the previous. Just look at the previous calculation. This is the exact same calculation as what we just did, so just repeat it. Mm-hmm.
If it's large, it favors the product.
I'm sorry?
If it's very large, it favors the product side.
Yes. Right. This exact same calculation, I'm just asking you to repeat it. Normally what you would do is you do it, but at home, you repeat the calculation. In this particular reaction, what percent, this is a question I ask often. What percent of the hydronium came from HCl, and what percent of the hydronium came from water? So when you look at this particular problem, the percent that came from HCl is huge. It gave 6 molar. Whereas the percent that came from water is minuscule. Water barely gave any hydronium. Do you see that? And so the percentage is quite small with the hydronium from water. Is it going to be the same in this next example? You tell me. Look at, is water going to be a significant contributor or negligible contributor to hydronium in the? And so all you're going to do is just repeat the calculation we just did, and then see how much hydronium comes from water. This is normally what I do. When I was a student, right after class, if they did calculation in class, right after class, I tried to repeat the calculation without looking at the solution, seeing if I could do it from memory. This would, the calculations we do in class are more important than the homework. You have to make sure you have mastered all the calculations we do in class in preparation for the test. You know, don't spread yourself out too thin. First, do all the calculations and make sure you know those inside and out, the ones covered in class, and then go to the homework. The homework are more diverse, usually. And that would be a good way to prepare. I think I lost the recording for this maybe, so I'm just going to have to force this to shut down. Hopefully the afternoon class recording will work.